So in this section, we'll talk about the comparison-based lower bound for sorting. And this is one of the gems in computer science, that you can not only engineer some solution to a problem, but you can also have mathematical proofs that you cannot really go much beyond what you've already done. You cannot do much better than what you know. And I mean, this is not completely unique to computer science. I put this, the principle of conservation of energy in physics here as one thing. At some point, the efficiency of some engine is lower bounded by the fact that you can't have a perpetuum mobile and stuff. But the efficiency of actual combustion machines is far away from this theoretical limit. So there's still room to go for engineers to improve engines. And in computer science, I mean, this is also true, but in some cases, like for sorting, we have a matching lower and upper bound, and the distance between the two is really diminishing. So you can say we know the best possible way to sort, and the same best possible way to sort is actually practical. So this is, the theory is much closer to the practice in computer science in some of these algorithms. I think this is something that's not celebrated enough in computer science. We can build cool systems, and we can have meaningful mathematical proofs in mathematical models that are very close to saying, and this is essentially as good as it gets, even if you try to be ever so smart. Okay, maybe it's not unique, but it's a feature of computer science that I like a lot. So we can speak of optimal algorithms, even though that term might be a bit overused. Now, what is behind these lower bounds in computer science? If you unwrap this, it is a statement about all thinkable algorithms, because you're saying every algorithm needs at least that many comparisons to sort. That would be the statement that we're looking at. And what's behind this is a way to say, what is that all algorithms? We have to make a way, we have to formalize this. And for this, you need mathematical models. That's again something, I stressed this in unit 1, I guess 5 times, but one more time won't hurt. Mathematical models are not just to torture you, they're really useful because they can prove these lower bounds. And one model we've seen is the word RAM model. So you can say all algorithms is all possible algorithms on a word RAM. That's a formal way to do it. It's a good way to do it, but it's one where the lower bound proofs become absurdly complicated. So people usually go to a simpler model, where the algorithms are a bit more restricted in what they can do, but the lower bound proofs become easier. So let's make this concrete. What we do in our case is we say, instead of talking about arrays and words and bitwise operations and all that, we just allow the following 2 operations. We can compare 2 elements. So we're given an array. The machine it's a custom built sorting machine. It can only do sorting. It starts with an array. It can take 2 elements and compare them. And the other operation is it can move elements around. So we can have some leeway how we do this. We can swap elements, or we can allow extra space or read the value from here and write it here. That's okay, because the cost of a program on this comparison machine is only the number of for the proof that we'll see, is only the number of comparisons. You can count those 2, but for the interesting sorting methods, one is within theta of the other. What's good about this model is that it makes very few assumptions about what we're doing. So it's very general in terms of the objects that we're sorting. So you can apply it to many scenarios. And the algorithms that you study here are general. Another good thing is that the algorithms we've just seen, they fall under this model. You can formulate merge sort and quicksort in this abstract comparison-based world, because all they do is they compare 2 elements and they move elements around. And the last good thing about this model, it is so restricted that if you only count the comparisons, every program on this machine, on this comparison model machine, can be written as a decision tree. So what this is, we'll see an example on the next slide. I stressed we count only comparisons and ignore the data movement because they will dominate in the statements we make. Let me show you the example first, and then we may come back. So here's a concrete decision tree for sorting the absurdly big array of 3 elements. And the way to read this is as follows. The algorithm says you're given an input, and the first step you do is you compare index 0 and 1. And then there's 2 possible outcomes. Either a 0 is smaller or not. So if it's smaller, you go to this branch. Otherwise, you go to the other branch. And then again, so these 2 happen to be the same comparison. They compare 1 and 2 on both sides, but that's not enforced. They can be different. Okay. So again, if this was the case, then you do another comparison. And if this comes out as less or equal, then you actually know the original order of the input because you basically checked for sortedness. 0 was less than 1 and 1 was less than 2. That means they're already in order. And there's a symmetric case. If it comes out the opposite way, then the input must have been, like this permutation, completely inversely sorted. And for the 4 other ways how you can order 3 elements, there's also 1 outcome. Okay? So just to stress these parts a bit, the nodes in this tree are individual comparisons. The next comparison can depend on the outcomes. So the different subtrees need not do the same comparison, even though in the example they do. The child links left and right are the outcomes of 1 comparison. And each leaf at the bottom of the tree is 1 possible order of the input. So one thing to stress here is this is 1 comparison tree. Now, what is this in terms of an algorithm? It is 1 concrete algorithm for 1 concrete input size. Okay? A decision tree like this is always tailor-made for lists of size 3. But that's okay. We can say an algorithm that works for arbitrary list sizes, it induces 1 such tree for every input size. And the tree has to be different because it's getting bigger and bigger. But for the usual algorithms, it has a certain kind of structure that you can figure out if you want. So 1 comparison tree is 1 algorithm on a specific size. Okay? And if you fix a size, the different comparison trees give you all different possible algorithms. Now, why do we like to force ourselves to think in these terms? Because this way of representing an algorithm allows us to analyze what's going on. One point is if you want to know how costly is an execution of this algorithm shown in this tree on a specific input, then you say if the input was actually ordered like 213, you would have to follow this path. And well, you run through 3 comparison nodes. So the algorithm used 3 comparisons in this case. And in another case, it used only 2. So the number can vary, and that's just the depth of the leaf in the tree. Which also means the height of the entire tree is the worst case number of comparisons. And by extension, if you want it, I think it's not on the slide, but still true, if you take the average depth of the leaves, that's the average complexity of the algorithm. And well, the highest leaf is the best case. I mean, once you understood that the depth is the number of comparisons, I guess these statements are not so hard. Another observation now that's obvious from the example, these decision trees are binary. Every comparison node has just 2 outcomes in this model. So if we have a tree with L leaves, we need to have a tree of height log n, log L rounded up. It's the same argument as we've used for binary heaps. The thing is, if you fill the heap, the best case you can have in terms of height is every level is completely full, and then the analysis from heaps applies. So the height is at least log L. And now comes the last crucial step. If we want to correctly sort any list of n items with such a decision tree, so if the decision tree is to represent a correct sorting algorithm, then it must have one leaf for every possible ordering of the input. Because if it would not distinguish all possible orderings, it can't possibly sort correct. It would treat two inputs the same that are differently ordered, so that can't really work out. Which means the number of leaves must be at least n factorial. That's the number of ways to order n elements. And so by putting this together with that, the height of such a decision tree has to be at least log of n factorial. And now that can be evaluated to be asymptotic to n log n. That's where all this n log n comes from, because log of n factorial is roughly n log n. Okay. You can make this statement more precise. Sometimes that's useful. I won't obsess about this too much. An immediate observation is that merge sort uses asymptotically n log n comparisons. So it is an optimal sorting algorithm in the worst case for the number of comparisons, and not just theta n log n, but precisely 1 times n log n plus lower order terms. So in the tilde asymptotic, it's optimal with the correct leading factor, the constant factor of the leading asymptotic term. Okay? Remember, we had this 2n log n for merge sort, where I said, remember 2n log n for merge sort? That was the number of element visits or array accesses. And here I'm counting comparisons. So the factor 2 comes from this distinction. If you merge, you have to read everything once and write everything once, but the comparisons is only 1 per element. And that's the problem that I stated on the motivation slide already, more precisely stated. It's not clear if we have an algorithm that is, according to this more precise lower bound, optimal up to a little O of n term in the number of comparisons. Although I might have to update the slides. There was some progress on this very recently, like last year or the year before. Must have been in the time since I last taught this. But this has not been peer reviewed. It's an absurdly complicated algorithm and no one knows if it's correct. I think that's the state of the art still. But at least someone claims they have found such an algorithm. And so pushing this boundary a little further. All right, to wake you up a bit and take this a little bit back to the concrete realm. There's a comparison tree on the previous slide, this one. And the question is, can you do better? Can you find, in terms of the worst case, another comparison tree for 3 elements that uses fewer comparisons? People voted. Three, 2, 1. That didn't lock. Oh, come on. And that's correct. It is optimal. You can't do it with fewer than 3. There's different ways to prove it. I mean, the easiest is probably just insert into the lower bound.